In about 4 billion years, the night sky over Earth, if Earth is still habitable, will be dominated by a second Milky Way, rising like a ghostly twin. The Andromeda Galaxy stretched across the sky, filling it from horizon to horizon. Right now, Andromeda is about 2.5 million light-years away. That means its light has been traveling to us since long before Homo sapiens existed. But gravitationally, it's already in our neighborhood. Measurements of its motion using the Doppler shift of its stars show that Andromeda is barreling towards us at about 110 kilometers per second. That's roughly the distance from New York to Philadelphia every second, sustained for billions of years. On human timescales, that feels like collision. On cosmic timescales, it's more like a slow, intricate dance. Both galaxies, along with dozens of smaller ones, are embedded in a common halo of dark matter, an invisible, massive scaffold that provides the gravitational glue of our local group. As the Milky Way and Andromeda orbit within this dark matter well, they lose orbital energy through a process called dynamical friction. That's not friction in the everyday sense, no rubbing surfaces, but a gravitational drag. Each galaxy plows through a sea of stars and dark matter, creating a wake of slightly overdense material behind it. That wake tugs backward, stealing orbital energy and angular momentum, slowly tightening the orbit until a near pass becomes an inevitable merger. When the first closed passage happens, the galaxies will be thousands of light years apart, center to center, but their outer disks will interpenetrate. Strangely, despite the word collision, almost no individual stars will hit each other. The average distance between stars in a galaxy is so large that they're like grains of sand separated by kilometers. The drama plays out in gravity and gas, tidal forces. Differences in gravity from one side of a galaxy to the other will stretch both spirals, flinging long, luminous tails of stars and gas into intergalactic space. Clouds of hydrogen will crash into each other, compress and collapse, triggering intense star formation called a starburst. Over a few billion years and multiple passes, orbital paths of stars will be scrambled. The graceful spiral patterns erased. The end product, a single, more spheroidal system, often called Milkdromeda by astronomers, a giant elliptical-like galaxy at the heart of the local group. At each galaxy's core sits a supermassive black hole, about 4 million solar masses in the Milky Way, and perhaps 100 million in Andromeda. As their host galaxies merge, these black holes sink toward the new common center, again by dynamical friction. They form a binary, orbiting each other at relativistic speeds, emitting gravitational waves, ripples in space-time predicted by general relativity and now directly detected by observatories like LIGO. Over time, the binary shrinks. The gravitational waves intensify, and in a final fraction of a second, the two horizons merge into one, releasing more energy and gravitational radiation than all the stars in the new galaxy emit in light during that instant. If we zoom out beyond our local group, a different story unfolds. Observations of distant supernovae in the cosmic microwave background show that the universe's expansion is accelerating, driven by something we call dark energy, a kind of energy of empty space itself, with negative pressure that pushes galaxies apart. On timescales of tens to hundreds of billions of years, gravitationally bound structures like the local group will stay together, but everything not bound to us will recede faster and faster. Eventually, distant galaxies will cross a kind of observational horizon. The expansion of space will drag them away so quickly that their light can never reach us, no matter how long we wait. Future astronomers born inside Milkdromeda may see only their own merged galaxy surrounded by dark. They will have no direct observational evidence that the wider universe ever existed. Within Milkdromeda itself, star formation will gradually exhaust its fuel. The easy cold gas will be used up or heated and blown out by supernovae and black hole activity. Each new generation of stars will be poorer in number, richer in heavy elements, and on average, smaller and longer-lived. After about 1 trillion years, almost all bright, massive stars will be gone. The universe will be populated by red dwarfs, cooling white dwarfs, neutron stars, and black holes. Galaxies will not end with an explosion, but with a long, asymptotic fading, entropy slowly winning as structure becomes more diffuse, more mixed, more uniform. Galaxies, then, are not permanent cities of stars, but temporary patterns in a changing universe, born from density ripples in the early cosmos, reshaped by gravity and feedback, and ultimately eroded by expansion and time. But to really understand their fate, we have to go back to the beginning, to the tiny quantum fluctuations that seeded every galaxy that ever was, or ever will be.